The speedometer needle is frozen at 200 kilometers per hour. The highway barrier is only a few meters away. No matter how hard you fight the steering wheel, the impact is inevitable. You are racing toward the millisecond where steel strikes steel. Yet, in that precise moment, before the sound of the crash even reaches your ears, an extraordinary anomaly occurs inside the cabin. A sharp, controlled burst of pink noise fires from the speakers. Before your brain's fear center can register panic, this calculated frequency triggers the stapedius reflex. The tiny muscle inside your middle ear contracts, locks the eardrum, and shields you from the deafening shockwave about to unfold. This is the limit of over-engineering, the legendary Stuttgart genius hacking human biology like an operating system. But how did this luxury empire, once capable of designing an acoustic blast to protect a passenger's eardrum 30 milliseconds before impact, end up decades later in a crisis room ruled by accountants, condemning its 100-year reputation to rusting metal tearing apart on the highway? I'm Halil Ibrahim. I am a mechanical engineer with 10 years of experience and a quality manager in the automotive industry. Today, I enter the scene with my auditor's notebook, my blue inspection light, and a forensic magnifying glass. Our mission is to dissect the golden age of automotive history, when the concept of cost was forbidden at the engineering desk, and then expose the corporate betrayal that followed. Today, we are investigating the legend of German engineering, Mercedes-Benz. This is not just a story of old cars. It is the documentary of the last great victory engineers won against accountants, and the tragedy that followed when executives sold the brand's soul to shareholder profitability. In the coming minutes, we will put everything on the table: wiring harnesses that crumbled inside engine bays under the mask of environmentalism, and spring perches that snapped on the highway, dropping the body toward the asphalt. But first, we must understand exactly where this obsessive perfection gene was born, and in which dimly lit workshop it first appeared. Tighten your seatbelt, take your tea or coffee with you. We are opening a massive forensic file together. When you look at a W124 from the outside, you see a calm, boxy, almost severely disciplined sedan. There are no exaggerated lines, no aggressive spoilers, and no fake air intakes shouting for attention. The genius behind this design was Bruno Sacco, the chief designer who shaped Mercedes-Benz's golden age. His philosophy was clear: a Mercedes-Benz must always look like a Mercedes-Benz, and a new model should never make the previous one obsolete overnight. He applied horizontal and vertical affinity. A 190E, an E-Class, and an S-Class had to be instantly recognizable as members of the same noble lineage. But the real miracle of the W124 was not in its visible design. It was hidden in its invisible aerodynamic intelligence. In the 1980s, the world had not fully recovered from the oil crisis, and fuel economy was vital. Mercedes engineers sculpted this boxy sedan in wind tunnels for years. When that large sedan emerged, its drag coefficient was an astonishing CD 0.28. 15 years later, cars like the Ferrari 360 Modena and several Porsche models were still around, CD 0.33. Despite its upright dignity, the W124 cut through the air like a projectile. How did they do it? By calculating every millimeter. The angle of the underbody panels, the shape of the mirror housings, the subtle V profile of the trunk lid, and even the openings in the wheel covers that cooled the brakes without disturbing airflow. Everything had a measured aerodynamic purpose. The rear surfaces were shaped so the air could detach cleanly instead of collapsing into a turbulent wake. Thanks to this aerodynamic discipline, even at 200 kilometers per hour on the Autobahn, you barely heard wind noise inside. Even the air leaving the body was engineered like a controlled process. The least known part of this aerodynamic obsession was the side mirrors. From the front, the W124 reveals something strange. The driver's side mirror is tall and rectangular, while the passenger side mirror is smaller and almost square. This was not a manufacturing error or a missing part. Engineers calculated optical angles and blind spots, then realized the right mirror did not need to be as large as the left one. By making it smaller, they reduced drag and made the car easier to park in narrow European streets. There was no joke here. Not a single millimeter of function would be sacrificed for aesthetics or symmetry. When people think of the W124, the first visual spectacle is undoubtedly the massive single windshield wiper. Most manufacturers simply used two cheap standard wipers. Single wiper systems often left the upper corners dirty. So what did German engineers do when money was not the first question? They placed an eccentric gear and telescopic linkage at the center of the mechanism. Let's analyze this kinematic genius. As the arm swept across the glass, the mechanism extended the blade telescopically toward the upper corners, then pulled it back near the center so it would not strike the roof seal. Thanks to this complex geometry, one wiper cleaned 86% of the windshield. No production car of that era had achieved such a wiping area. Even today, many systems remain around 80%. Was it necessary? To an accountant, no. To an engineer, maximum visibility in heavy rain at Autobahn speed was a vital safety requirement. Now let's examine why this car felt like a flying carpet. When a W124 entered a broken road, it swallowed the potholes. Yet when it entered a fast corner, it never leaned and floated like a boat. The secret was its rear suspension, the 5-link independent rear axle, or in German engineering language, the Raumlenkerachse. While competitors used basic rear arms or torsion beams, Mercedes forged 5 different control arms for each rear wheel, controlling camber, toe, and wheel movement separately in 3-dimensional space. Designing this system pushed Stuttgart's CAD software for months. Its manufacturing cost was far higher than competitors' systems, but Mercedes management accepted it. Road holding and comfort could only be achieved together this way. Despite the brutal cost penalty, they made it standard across the range. But was this complex suspension geometry the only reason the W124 felt like a flying carpet? Absolutely not. The German obsession reached into the cabin as well. While competitors built seats mainly from foam and leather, W124 seats contained steel alloy coil springs. But the real madness was this: the oscillation frequency of those seat springs was mathematically coordinated with the working frequency of the 5-link suspension below the car. Why? So the movement of the chassis and the movement of the seat would not collide, amplify one another, or create a resonance that fatigued the passenger's body, caused nausea, or punished the spine on long journeys. The chassis and seat breathed at the same controlled frequency, like one living organism. This is pure engineering, the kind marketing brochures cannot explain, but quality assurance documents quietly certify. Comfort was not softness, it was controlled motion, measured against the human body. This uncompromising perfection gene did not appear from nowhere. When we go down into the dusty pages of automotive history, we find a sensational asymmetry that corporate marketing departments rarely tell. The famous star that shines today under one roof was actually the product of parallel geniuses who worked in different German cities and never met. Karl Benz in Mannheim, obsessed with system integration, and Gottlieb Daimler in Cannstatt, chasing the philosophy of universal power, together with his brilliant shadow, Wilhelm Maybach. Pause for a moment and ask like an engineer. Did humanity copy the idea of the internal combustion engine from nature? Of course not. Nature had no engine template. Engineers were inspired by a deadly weapon of the battlefield, the cannon barrel. You placed gunpowder inside the barrel, ignited it, and launched the projectile forward. The genius breakthrough happened here. If you attached a mechanical arm, a connecting rod, behind that projectile, and made the piston return continuously after each explosion, you would have a continuously operating mechanical power unit. Karl Benz's 3-wheeled Patent-Motorwagen, registered in 1886, worked exactly with this logic. But a massive process anomaly stood in front of us. The machine had a displacement of 954 cubic centimeters, almost the size of a modern 1-liter engine. So how could modern engineers extract hundreds of horsepower from 1,000 cubic centimeters, while this cast iron mass produced only 0.75 horsepower? The thermodynamic power data gives us a clear answer. The key limitation was engine speed. The N parameter could not pass 400 revolutions per minute. Why? Because the battery, distributor, and spark plug had not yet been invented. To ignite the air-fuel mixture, an open flame had to burn constantly on top of the engine. When a mechanical valve opened, this flame entered the cylinder and ignited the mixture in a primitive way. The moment you exceeded 400 RPM, the flame either died out or the timing went completely wrong. The entire engineering theory was trapped by primitive ignition technology. And what about the 3-pointed star, the emblem that whispers luxury and status every time we see it? Did that elite vision of dominance on land, sea, and air really come from a design studio, as corporate historians claim? Yet the surviving forensic archives make this corporate myth far more complicated. In 1872, while Gottlieb Daimler was still technical director at the Deutz factory, he sent his wife Emma a New Year's postcard showing Cologne Deutz. On it, he marked his house with a rough three-pointed star and wrote, "One day, this star will shine over our factory and symbolize our prosperity." So the billion-dollar symbol of luxury was, in origin, a romantic home location mark drawn by an engineer for his wife. Or perhaps it was not that simple. Absolute historical certainty on this subject is no longer realistically possible. And what about those W codes at the beginning of every model? Why do legendary chassis names begin with W124, W140, or W210? This is a simple but powerful trace of German industrial standardization. The W comes from Wagen, meaning automobile or vehicle in German. Every new chassis project in Stuttgart was registered as a Wagen project and sealed with that code. It became a single industrial reference linking every drawing and process from body metallurgy to assembly line torque wrench calibration. But one point in our process checklist remained dark. As this 0.75 horsepower, open-flame three-wheeled machine rattled through Mannheim, the public mocked it. Why would anyone need such a dangerous machine while horse carriages existed? Benz's financial collapse had become only a matter of time, until one woman quietly opened the door of that dim workshop at 5 o'clock one morning. At exactly 5 a.m. on August 5, 1888, Karl Benz's wife, Bertha Benz, secretly rolled the three-wheeled mechanical machine out of the workshop while her husband was still asleep. The people of Mannheim mocked it as an unlucky horseless toy, and the project had pushed Benz toward bankruptcy. Bertha was not merely leaving to visit her family that morning. She was launching the first and most radical product validation and environmental field test in automotive history. The brutal 106-kilometer route would become a moving laboratory, transforming a brilliant engineer's fragile workshop prototype into a commercially credible machine. That dawn journey would force theory to answer to reality. Now let's open our auditor's notebook and examine the major failure modes Bertha faced. The vehicle had left sterile workshop conditions and entered the real environment. Rough roads, poor fuel, dust, heat, and unforgiving mechanical limits. In the first hours, the engine began to misfire and lost power. The root cause pointed to Ligroin, a cleaning fluid sold only in pharmacies and used as fuel. When you are the first of a technology, you must accept that not only the machine but also the infrastructure feeding it has not yet been born. There was no proper filtration unit in the fuel tank. Sediment clogged the tiny carburetor jet. Bertha had no formal engineering education, but she had a genuine problem-solving reflex. She pulled a long hairpin from her hair, pushed it into the blocked passage, cleared the sediment, and restored the fuel process at the roadside with no formal tools. Now we climb the next step of the tension ladder. As the journey continued, the high heat radiating from the engine block and uncontrolled transient vibration from the chassis triggered another systemic weakness. The insulation around the primitive electrical wiring melted, leaving the copper wire exposed. When the bare wire touched the chassis, it short-circuited, and the ignition stopped. Bertha realized she had to isolate the current and found the only available insulation material on her own clothing. She removed the leather and fabric garter holding her stockings and wrapped it around the exposed wires. The industrial ancestor of today's high-temperature harness sleeves was born that morning from a garter, sacrificed on the Black Forest roads. But the greatest mechanical crisis erupted on the steep hills of the Black Forest. The vehicle stalled on the incline, the engine faded, and the wheels began rolling backward against the gravity vector. Bertha had discovered a new design constraint. Karl Benz had designed the car using the flat Mannheim planes as the reference condition, so the torque transferred from the crankshaft to the wheels could not defeat gravity on steep slopes. The vehicle could not climb safely, and on descents, it became a death trap. When the brake lever was pulled, wooden blocks pressed against the rotating iron wheel rim. The conversion of kinetic energy into heat exceeded the thermal limit of the wood within seconds. The blocks scorched, friction disappeared, and the brakes failed. Bertha found the permanent solution in a village cobbler's shop. She had thick, durable leather fitted onto the brake blocks, creating a replaceable sacrificial friction surface that could absorb both wear and thermal energy. At that moment, one of the greatest safety milliseconds in automotive engineering was born. That sacrificial piece of leather, preventing direct wood-to-metal friction and absorbing wear and thermal load to protect expensive parts, became the functional ancestor of the world's first brake pad. When Bertha reached Pforzheim, she sent her husband the famous field feedback telegram. When Karl Benz examined this failure data in his Mannheim laboratory, he had to radically revise the design. This was the step that transformed a prototype toy into a commercial vehicle ready for production. Second and third gears had to be added immediately, so the engine would not stall under heavy loads and torque could be multiplied against gravity. Without the failure data from Bertha's uncontrolled field test, the engineering world might never have entered the age of analog perfection. Genius at the design desk matured only when it collided directly with the raw, uncontrolled truth of the road. When the field data reached the laboratory, the calendar had moved toward the beginning of 1900. While Benz dominated the domestic market, a shocking crisis was about to erupt in Nice, rewriting the fundamental baseline templates of modern automotive design. On March 30th, 1900, two Daimler Phoenix racing cars personally ordered from DMG by Nice consul Emil Jelinek entered the road. Factory driver Wilhelm was behind the wheel. At the first sharp corner of the La Turbie hill climb, the car lost control within seconds, rolled over, and cost Bauer his life. The next revolution would begin with a fatal nonconformity. If we examine the crash like a quality auditor entering the scene with a dimensional control checklist, we see that the geometry itself was the primary physical weakness. Vehicles of that period were built by mounting huge vertical engines onto horse carriage chassis. The ratio between the Phoenix model's track width W and center of gravity height H violated the dynamic stability threshold. When the car entered the corner, the lateral centrifugal force instantly defeated gravitational resistance. This fundamental geometric weakness turned the car into an unstable death trap in the middle of the road. Jelinek furiously knocked on the doors of DMG, the Daimler Motor Company in Stuttgart. The financier standing in front of them was not an ordinary customer. He had the power to buy the factory's entire production capacity with one signature. He placed a clear commercial ultimatum on the table. You will build me a machine that will not roll over in corners, with a low center of gravity, a low body, and a long stance. If they succeeded, he would pay a fortune for 36 cars and effectively finance the factory's entire next industrial chapter. But he had one more condition. This new machine would not carry the Daimler name. It would be named after his 11-year-old daughter, Mercedes, whose name he believed brought him luck. That is how the global symbol of luxury and performance was born. Not in a design studio, but in the post-mortem room of a racing crash and a commercial standoff. This ultimatum triggered one of the greatest paradigm shifts in automotive engineering. Wilhelm Maybach, Gottlieb Daimler's brilliant shadow, sat down at the design table and drew the first true automobile architecture in history. The Mercedes 35 PS Maybach threw the wooden carriage body logic into the trash. For the first time, he designed a low U-profile chassis pressed from 2mm steel sheets, reducing chassis weight by roughly 1/4 in a single analytical move. More critically, he moved the engine, which until then had sat above the front axle, down behind the front axle, and into the lowest point of the frame. This brought the H parameter of the engine mass closer to the asphalt. This placement overturned the lateral load transfer equation and stabilized vertical tire forces during cornering. The insanity of mounting engines onto horse carriages ended that day. In its place came the front mid-engine architecture that would become the genetic map of modern sports cars. Maybach also created another manufacturing revolution by casting the crankcase from aluminum alloy for the first time, rewriting the entire front axle weight distribution ecosystem. But one massive thermal weakness still had to be solved: heat management. At the heart of the Mercedes, 35 PS was a 5.9-liter inline-4 combustion chamber. At high RPM under load, the water inside the cylinder jackets boiled within moments, and thermal runaway began melting the engine from within. The car had to carry heavy water tanks, which increased front-end mass and damaged the center of gravity. To solve this thermodynamic constraint, Maybach developed the famous Honeycomb radiator. He arranged 9,000 small brass square tubes side by side to create a dense, industrial honeycomb matrix. Each tube measured exactly 6 by 6 millimeters. This brilliant process control multiplied the surface area touched by coolant. The formula was clear. The larger the surface area, the faster airflow could absorb thermal enthalpy. By keeping the flow regime inside the tubes in the laminar transition zone, Maybach optimized the thermal boundary layer on the brass surface. process, he reduced the required cooling water volume from 18 liters to only 9 liters in one decisive move. Freed from unnecessary front-end mass with reduced polar moment of inertia, the Mercedes 35 PS destroyed its rivals at the 1901 Nice races so completely that a historic sentence was spoken that week. Today in Nice, we entered the Mercedes era of the automobile. That pure genius at the design table, combined with Jelinek's commercial ultimatum and Maybach's Honeycomb radiator formula, created the first unshakable baseline of analog perfection. This obsession with part durability, passed down through generations, made Mercedes the indispensable mechanical fortress of taxi fleets across civilian roads. By the mid-1980s, Stuttgart's R&D rooms were completing the final process validations of the W124 project. Management ordered the shutdown of the W123 production lines and the transition to the new model, replacing what many drivers considered the most unbreakable and wear-resistant chassis in automotive history. On paper, it was normal product renewal. To the market, it looked like the possible end of mechanical immortality. On that day, one of the most absurd and magnificent worker boycotts in German industrial history erupted. Tens of thousands of taxi drivers arrived at the gates of the Sindelfingen factory in ivory-colored Mercedes W123s. They completely blockaded the line exits. Their message to the executives in the corridors was clear. We do not want to give up the W123's million-kilometer mechanical loyalty. We know you have started cutting budgets in R&D, and we know you will lower parts quality in the new car. The customer had turned the factory entrance into a live quality audit. The market was issuing a corrective action request directly to management. As engineers, to understand why the taxi drivers rebelled that day, we must remove the sump covers of the W123 and look at the metallurgical data. At its heart were the OM616 and OM617 naturally aspirated diesel engines, the mechanical immortality template of automotive engineering. The cylinder block was induction-hardened cast iron, and forged steel crankshafts rotated with almost zero wear tolerance at the bearing surfaces. The most critical point was the timing mechanism. The chain connecting the camshaft to the crankshaft had not been sacrificed to cost games. It was a heavy, armored, double-row duplex steel chain. Bosch's mechanical inline injection pump produced uninterrupted injection pressure for hundreds of thousands of operating hours with micron-level tolerances, regardless of the quality of the liquid entering the fuel line. Even if you poured vegetable oil into these cars, they had enough safety margin to pass 1 million kilometers without bending a valve or breaking a piston ring. Taxi drivers sensed that plastic components, lightweight alloys, and electronic circuits were beginning to infiltrate the engine bay of the W124 project under the mask of cost reduction. Facing this brutal market audit, corporate management had to retreat and keep the W123 lines open far beyond the planned schedule. These lifetime fortresses, built by engineers without counting pennies, were being coded as corporate threats in the Pareto tables of budget committees obsessed with after-sales parts revenue. As the 1980s closed, financial analysts secretly gathered in Stuttgart's smoky rooms, preparing to sign what would become the financial documents of engineering revenge. And an even darker shadow was racing down the Autobahn from Munich towards Stuttgart. Eternal rival BMW was launching an attack on Mercedes' unshakable throne with a civilian monster capable of shaking the sky and the earth. Its first production IS-12 engine, aimed directly at Stuttgart. Stuttgart's corporate pride was about to face a deadly anomaly. Over-engineering would have to enter the most expensive, obsessive, and insane revision room in its history. Munich had turned 12 cylinders into a declaration of war. The shocking file of the whale-bodied W140, the 18-day handmade logistical nightmare that ended on truck beds inside Porsche workshops, and the later cat-eye cars whose rusting structures could fail on the road like cheap tin. That complete forensic story is waiting for us in the next act. I'm Halil Ibrahim. To make sure you don't miss this and many more engineering investigations, follow the channel and turn on notifications. You can also support the work by liking the video and sharing it with your friends. Until we meet next week in the next act of our Mercedes file, take care and stay well.